Good morning and welcome to this breakfast seminar here at ITRL. My name is Albin Engholm. I will be the moderator for today's session. I'm a PhD student here at ITRL. ITRL is a research center here at KTH where we do research on to enable a more sustainable transport system. And one focus we have is to analyze the role of emerging transport technologies. We do interdisciplinary research, and we also focus a lot on bringing different types of stakeholders and perspectives together. So our breakfast seminars here is one opportunity to share knowledge, both from either from projects here at ITRL, or as today from external researchers in the field. So before I will present our speaker today and the topic, just some housekeeping. We are quite many joining today, so please be a bit cautious with this. Have your microphone muted until you wish to speak if you have a question at the end. Also, please keep your camera off until the end of the talk. You will have the possibility to ask questions to Jakob after his speech. And then you can either use the raise hand function or you can put your question in the chat. So if you have discussion questions, we'll take them after the talk. But if you have questions just for clarification, if something is unclear, you can write them in the chat and we will make sure that Jakob gets them and we can clarify. Also, please check out ITRL's webpage for upcoming seminars. We host those regularly on different topics in transportation, so please keep posted there. So, jumping into today's seminar. So we're going to talk about the electrification of heavy trucks, and more specifically about what role different types and combinations of different charging infrastructure can play. With us today to do that, we have the great pleasure to have Jakob Lugstadius from RISE. He's a senior researcher there. He has a PhD in computer science, and has also worked as a senior data scientist at Scania, and is now working on large-scale modeling of charging infrastructure. Today, Jakob will base his talk on a study he recently published called The Interaction Effects Between Battery Electric Trucks, Electric Road Systems, and Static Charging Infrastructure. So, as you know, the last years we have seen a quite big momentum catching up for electric transport and the electrification of heavy transport. And it's now clear that it will be a key solution for decarbonizing the road transport system. However, one challenge and issue that's always been pointed out is how to achieve efficiently a large-scale charging infrastructure system. And we can broadly separate between two types: static charging, which is where we have fixed charging stations, or dynamic charging, or what are more often called electric road systems, where you can charge a vehicle while driving dynamically. And it's been a long discussion on what type of system to choose and how a good combination of these two systems look like. And there have been multiple studies coming to somewhat different conclusions on that. One example is that the Swedish Transport Administration got a government assignment a few years ago. They pointed towards a direction more with static charging and biofuels, but other researchers and other studies have come to different conclusions. And it's not kind of weird that we get a bit different takes on this, because this is a really complicated system and a different question to say something intelligent about. It's a large infrastructure system, either if it's static or dynamic, but maybe particular for dynamic systems. We have a high fixed costs, some network effects, and also an economy of scale. So we need enough users to cover the cost. But knowing how many users there will be is quite challenging, because we need to then consider what are the costs of the other alternatives and how are the other technologies developed. But there's also a lot of actors involved here and whose decisions we need to account for. It's the fleet owners and their investment decisions in different vehicle types. It's the transport operators and what vehicles they will choose and how do we route them. And we also need to understand how this fit into bigger logistics picture. So it's definitely complicated, and there's a need to take a systems approach. And I think that's why one of the reasons we have invited Jakob here with his work on trying to capture some of these complexities and some of the interactions. And I think it's an interesting example on how you can use large-scale modeling to try to account for that. So with that as a background, I'm happy to hand over to Jakob. Jakob will talk for, let's see if I can show the slide. Jakob will talk for around half an hour until 9:10, and thereafter we will have around 20 minutes for discussion and questions. So yeah, here we go. Stage is yours, Jakob.
Thank you. Very good introduction. So Albin mentioned this is a study about the interaction effects specifically between different types of charging infrastructure, dynamic and static charging infrastructure, as well as battery electric trucks, and specifically the batteries. As background, Sweden has a target to decrease greenhouse gas emissions from road traffic by 70% by 2030. By 2019, we had achieved a 20% reduction, but that was primarily through mixing of biofuels, which essentially means that we need another pathway to reach this much more ambitious goal. And we are on track with registrations of passenger cars, except for the past year when we have removed a lot of subsidies, reduced taxes on fossil fuels and so on. Therefore, we have broken this pathway. Still, I believe that electric cars have sufficient benefits that they will take over pretty soon. But it does require something. It requires infrastructure. And the way you build that determines what kind of vehicle you have, how expensive the vehicle will be, how you shift cost between infrastructure and vehicle. And the current approach for heavy trucks is that you go for depot charging, public fast charging stations, and very large expensive batteries. Electric road systems have been proposed as an alternative. It's different technologies. This study does not focus on any one technology. In fact, my impression is that these technologies cost about the same, given that you parameterize them in a lot of different ways. But you can have basically power from underneath the vehicle or power from above the vehicle, being those two that are considered in Europe. So when I speak about interaction effects, I'm talking about, for instance, substitution effects, that you build one type of infrastructure that replaces the other, competes with the other. You have geographic effects where you build something in one area, something happens somewhere else, positive or negative. You have changes in utilization. So you had infrastructure of some kind and you add something. What happens to what you already built? And as you build different types of infrastructure, different placements, different density, so on, how should a cost optimal vehicle be adapted to suit the new infrastructure? And also, we can expect quite rapid advances in battery technology, or at least quite significant advances over the lifetime of infrastructure. We're talking about maybe 30 years for some infrastructure. And is it then the same infrastructure that is attractive both at the beginning and the end of the lifetime of the infrastructure, or does it change? We could spend easily 30 minutes on methodology, but I would like to highlight some of the differences or qualities that I think this work has compared to a lot of other work. And that is a combination of considerations. It considers 4 different heavy truck classes, from 16 to 60 tons, and they share infrastructure. It looks at the entire Swedish road network, not only a very simplified road network, but actually all of the roads are in there. And on this road network, millions of transport routes overlap. I have not had access to any actual GPS traces from vehicles, but you will see what data was used instead. There are combinations of different charging infrastructure, 3 types of static infrastructure and electric roads, and how much you build of this infrastructure, as well as how much you charge for the use of that infrastructure, is all in balance through an adaptive simulation. And this infrastructure gets built over time, so it's possible that you outcompete something and then you have stranded assets that, for instance, either raise prices because you need to pay off something with fewer users, or you have something that simply goes bankrupt. Battery costs are considered as a lifetime cost, so an annualized, levelized cost, meaning that if you have a large battery that lasts longer, that can have the same cost as a small battery that lasts a short time. And tax revenue, as we switch from fuel taxes to electricity taxes in the currently today, those are not the same. So we cannot compare and say that we have the same cost if we change the government revenue from the transport system. So therefore, there are no electricity taxes in this, but rather I've converted all of the current fuel taxes into kilometer tax, of which part is CO2 tax, and that CO2 tax is proportional to the amount of CO2 that you emit. I think I will start with this one. I mentioned that I have not had access to GPS traces from vehicles. Instead, we had routes, so a giant origin destination matrix taken from some goods. This is based on goods flows initially, saying this much goods flows from one municipality to another. We use population density to sample within the municipalities. We don't get all of the origin being in the same point. At least we have some correlation of where, at the very least, cities are. It's not perfect inside cities. And then we route using OpenStreetMap for each of those combinations. And then the gray bars here show the resulting amount of traffic when we aggregate all of these routes on the road network versus the measured traffic from actual AEDT measurements on the, so Trafikverket's official data about traffic on the roads, heavy traffic. We do underestimate traffic inside cities quite substantially. We believe that is due to lack of buses in the data set, but we cannot prove that because they would still fall within the Trafikverket's data set, but not in ours. The simulation model then, we feed in a lot of, it's a scenario-based, agent-based simulation tool that iterates until convergence. And it does this for different 5-year periods sequentially. So it's a build out over time, inheriting infrastructure from the previous year. Vehicles are not inherited; those are adapted to the new year. We feed in a lot of. We have an initial estimate of charging price. Feed in all of this route data. Feed in a lot of parameter values, saying what electricity costs, what fuel costs, and so on. An order of infrastructure construction. This is an order only, not which infrastructure to construct or how much. It's only if you build a lot, you build it in roughly this order. And then scenarios saying how much infrastructure are we looking at? Are we looking at building out 3,000 kilometers until 2045, or what is the plan here? And why is this an input? Well, it's because very quickly when you start modeling this, you see that electrified trucks are much cheaper to operate than diesel trucks. So you cannot really say that you will have infrastructure meeting demand. It's the other way around. Because if everybody could have as much infrastructure as they wanted today, it would already be there. Then for each of these transport routes, the combination of different charging strategies and battery capacities that gives the lowest transport cost. So kilometer cost or analyzed cost, or however you want to measure it, is chosen. That is aggregated up onto a total infrastructure demand, which is then iterated back to estimate the charging price based on that infrastructure. And then this iterates on the convergence. And finally, we can aggregate this into lots of different figures and scenario comparisons, as you will see. When I mentioned order of infrastructure construction, this is there's one order for electric roads, starting down here in the south of Sweden. And then the road segments that are most used by the vehicles that could already be using electric road are added gradually until we have this map. So if you build 4,000 kilometers of electric road, then you can only place within everything that is these shades up until some yellow-green. We can see on these maps that road segments inside cities get included quite early. And because we have low correlation with traffic inside cities, I wouldn't trust that it's exactly these road segments, but I would trust that if you build out electric roads, you should probably consider urban electric roads very early in the plan. For fast charging stations, the order is in amount of traffic. So we start where there is most traffic. For depot and destination charging, it's random. So there is no correlation with geographic placement, meaning that it's assumed to be primarily limited by local grid capacity, which is not planned for where you have your current depots. There are a lot of parameter assumptions, about 400 in total. I will not go through them all. The main assumption, I would say that the two main assumptions that we really need to know about. One is that static charging is not really assumed to have a scale benefit. I cannot find any source that claims it does. Intuitively, it would seem it does, but I cannot find any such source. So it's pretty much a linear cost. There's a small base cost. If you build it way too small, it doesn't make sense. But primarily it's a function of utilization, not in terms of how much you build. Electric roads have a high upfront kilometer cost and then a small marginal cost for extra power. The other main assumption is that combustion engine vehicles are expected to have lifetimes of 7 to 10 years, whereas electric vehicles are supposed to have that, expected to have that today, but gradually they have a longer lifetime. This is Scania and Volvo managed to kind of agree on this after many conversations back and forth. But this has the effect that vehicles become cheaper as an annualized cost over time. And of course, that benefits the transition to electric vehicles.
The technical lifetime.
Yeah, this is really hard. Like, what should you measure?
Yeah.
So it's some kind of economic lifetime.
Okay. I would say it needs to be an economic lifetime.
Yeah.
The technical lifetime, when we talk about one of the brands, they never die, they just grow. Which one?
Yeah, so there was a remark here from the audience that it has to be the economic lifetime. We can discuss what happens later if Europe wants to keep all the batteries and so on. I don't really know. That's a really complex question. At least this is an assumption in this study that explains some of the results. Key limitations. There's only battery electric vehicles, battery electric heavy trucks, and internal combustion engine heavy trucks. There are no fuel cell electric vehicles, there are no hybrids, there is no light traffic. The first, I would say, exclusion of other than BEV and ICEV mainly simplifies the research, reduces cost in the calculations. The exclusion of light traffic greatly penalizes low power electric road systems that may be sufficient for passenger cars, but not for trucks. And it also penalizes urban electric roads. So if there is an order of build out in this system that recommends that you still maybe start building the highways, I cannot say that is the case if you include passenger cars. What else? We mentioned some of this. Yeah, there is an implicit assumption in the model that you have similar infrastructure, equivalent infrastructure abroad. Because many of the routes that traverse Sweden, they also have a large component abroad. Then you need to make assumptions of what is there. And then it's essentially, yeah, if you have access to something in Sweden, you have access to it abroad as well. In equal proportions. And there are no interaction effects. We're going to see that there are no interaction effects with traffic volume, electricity prices, and battery prices, meaning that how we design this system does not impact these. We can assume that if we have lower transport costs, we will get more transportation. But how that should be modeled, I don't know yet. Very happy to get feedback if somebody else has good input on that. Also electricity prices and battery prices, we would assume that demand in some way controls these. I don't know if transport is enough to impact electricity prices, but definitely battery prices. Sweden might not be enough, however. First, for a sanity check, what can we get? If we run extreme scenarios in this model, we run no charging infrastructure at all. Then we have an assumption that we have a gradual mixing of biofuels, increasing internalized costs, and a decreasing cost of CO2, which with Sweden's very high valuation of CO2 means that we have a stable cost over time. In another country, say Germany, then you would have an increase in cost over time if you assume this with a lower valuation of CO2. If we run only static charging infrastructure, we have a decrease in cost with eventually half the cost being made up of driver costs. Quite strong incentive for autonomous trucks, I would say. If we also add electric roads, if you look very, very carefully, you have a slight decrease in cost, but it's very minor. Because frankly, the main cost that you can reduce, you could potentially reduce driver costs, but those strategies that add up to very high driver costs where you stop and make lots of extra just pure charging stops, those are already rejected based on cost, since everybody chooses the cheapest way to operate. Therefore, you have slight cost improvements, but not that much. If with 2020's cost parameter assumptions, we give 25% of routes the option of charging at depot, then we have a slight electrification happening. If we take the other extreme scenario, we just allow charging infrastructure everywhere with 2020's parameter assumption, almost all traffic would already have been electrified. I don't think this disagrees with literature. I mean, it's claimed in certain ways here, but I haven't seen anything that really, there's definitely a lot of stuff that agrees with this. So simply put, if you run hundreds of scenarios in this, the main correlation that you see is percent of electrified transport work correlates with system cost negatively, linearly. So if you see a figure later that says this is how much we lower transport cost, lower system cost, you can pretty much translate that into percent electrified traffic. There are substantial differences in how this is achieved. And we're looking at the qualitative differences now in what you can actually achieve, because many of these are unrealistic scenarios. So if there's not much difference in cost between electric roads, between a system with only static charging and a system with also electric roads, so it's not instead of, it's also, then we still see that so all the traffic here that is marked in yellow is part of a route that somewhere along that route makes use of electric roads. And that is all of it, wherever we have electric roads, except if you look very carefully at the boundary here, where it ends, then it goes down and you have an S-curve transportation, so that you have some of the traffic going up here, for instance. Well, that's probably not very many routes in this data set that we have. So those ones maybe go all the way down here. And then they will make use of electric road here, but there isn't any here, but that part they can still lower cost by using the infrastructure at this part of the one. There are anomalies in this data set, like I don't know what's going on up here, and we have some other things. But overall, we're looking at the interaction effects. I think it's good enough for that. So what competitive advantage then does it offer? It has to be something if you want to use it. The main conclusion I have is that electric roads enable you to choose a smaller battery. You can traverse your routes using a smaller battery if you have electric roads. You can still, of course, traverse it using a big battery. And if you do that, you can lower your transport cost by about 5%. 5% may sound very insignificant. If we look back at the distribution of costs within the total transportation cost, you cannot really lower it much more than that. 50% was already driver, and then you have the main part of the vehicle that isn't battery. Your maintenance probably not going to be affected on an electric vehicle by, or might increase slightly. So 5% is still quite significant. We also have margins in the sector that are somewhere around this. So if you compete with somebody else who can lower their cost by 5%, you might be forced to adapt your vehicle as well. If we look at this quantitatively, and now I wouldn't trust these numbers exactly, because they depend on how you allocate goods to different vehicles and which combinations of routes they take and so on. But in each cell, you have the percentage of routes in this entire data set that can be traversed, so where you can reach your destination, given that you have a certain battery capacity in 2030 and a certain charging strategy, where a charging strategy is simply, I will use this type if it's available. And here, everything that uses electric roads can go to much smaller battery capacities. But this one doesn't say anything about cost. If you want to look at how these costs differ, so for the very early years today, we're not looking at the lowest costs with the absolutely smallest batteries, but we do end up there quite quickly. But this is in the report. And we have combinations of contributions from reduced capital interest cost when we lock up less capital in a battery. We have reduced cost of calendar aging, meaning if we have a smaller battery, calendar aging will remove as much a percentage of capacity per year, so therefore we remove less if you have a small battery. A lower weight, this contributes somewhat to greater cargo capacity, not 100%, of course, but the rest will contribute to lower fuel consumption. And you have much more flexible stop locations. You no longer need to stop exactly where there is a fast charging station. You can stop wherever your driver needs to take their break. That, of course, relaxes your, it lowers your time to transport in a little bit. I do not see that smaller batteries due to electric roads will last a shorter time because they are cycled less. So because you have energy going directly from the road to the motor, you cycle battery less. So although it's smaller, the aging is about the same as the cycle aging is about the same as for the large battery. How does it affect the sizing of batteries in fact? We see roughly a 70% reduction in cost optimal battery capacity per truck. So without electric roads, we see what we roughly see on being offered today by the truck manufacturers, 450 to 1,000 kilowatt hours usable capacity per truck. If we add electric roads, that cost optimal capacity drops to around 200. Very strong support in literature for this, both for this like 50 to 70% reduction. There are studies from Sweden, Denmark, the UK, France, Turkey, Germany. This is just on a quick search yesterday. This is by far the most supported number in the entire research. What contributes to, if you want to forecast, like how much battery reduction do I produce in the entire system on an annualized basis, given how much electric roads I add, you need to consider that it's not about power. You need sufficient power for people to want to use it, but then it's just about how much you reduce the cycling. And you reduce the cycling based on how many road kilometers you build. So if you have an electric road with lots of gaps, it doesn't contribute much. It might be here somewhere, 20%. If you have a continuous electric road, you might have 50% reduction. And this, of course, if you were to do this for passenger cars, which probably contribute about 80% of the future battery use, so the battery amount of batteries locked in the transport system. If batteries is a limitation, you want to support light traffic. If that is your motivation to build electric roads. Interactions with other charging infrastructures. So this is if you have X and you add Y, what happens to the use of X? The main impact by far is that adding electric roads directly outcompetes fast charging stations. It can, in some scenarios, reduce demand by 90%. It's possible to have a positive contribution in this model, since you can actually add more enable more electrification, thereby adding more, making the cake larger, even though you might get a smaller share of the cake. But this is very, very slow. We see some impact also from depot charging and destination charging. But these are in different scenarios. It's basically if you have so much that you can choose, then you will choose depot charging. One risk that emerges is when you look at build out over time, in the way that charging stations are built in this model. I said that the build out order is based on ADT, so traffic density. That means that you will initially offer some charging stations. And then because electric vehicles are cheaper to operate, there's very high demand for that charging. So these become very large, very high capacity. Gradually, as we add more infrastructure in the system, including depot and destination charging that isn't on this map, we get many more options to charge. And then the demand for so much charging at these first spots decreases. So they actually cannot cover their costs and they die out. And we end up with a system with many small charging stations, fast charging stations, and an electric road system that is largely unaffected by this densification of the other infrastructure. I think a very powerful conclusion from this is that the electric road that you build, if you consider now as a planner, which electric road should I build? I don't know anything about how this system will develop. Are these operators going to build out this much charging infrastructure of other kinds, or will it be scarce, where will it be placed, and so on? It doesn't matter. The best electric road to add is always the same. So your best move is always the same, regardless of what the others do. And that is, it doesn't matter which of these alternatives you choose. They are all a very long electric road. It says 6,000 road kilometers, but then there's some other optimization going on here. So it's up to a 4,000 kilometer road network being covered with some amount of gaps. And as long as this offers an average power per vehicle per kilometer, so including the gaps, of 150 kilowatts, then you're fine. Beyond that, you're mainly starting to fill up batteries very quickly. So if you build a 700 kilowatt road per vehicle, then okay, they will fill up the battery quick, and then they will still not charge more. This is a very complex figure to interpret. I'm still trying to figure out what it actually means in terms of what we should do. It shows at different stages of electrification. So if we have achieved the 20% electrified transport work, how much system cost reduction do we get by investing €1 in some type of charging infrastructure? This figure changes a bit depending on which year you draw it for, because you have different parameter assumptions. And especially the battery costs start moving the blue dots up and down. But what it shows is that early on today, by far the greatest return on investment is from electric roads and depot charging. Later on, you should add a lot of small fast charging stations. I believe if you add the passenger cars to this, the blue lines would go way up, maybe up to 30 or something. But I haven't run that yet. It's just when I look at the math I've done, it should impact it some way like that, probably. As you add more charging infrastructure, now you cannot see anything because of all of this stuff at the top, but this says sparse static charging. It says moderate static charging, dense static charging. It means in this scenario, you have depot charging at 10% of routes, destination charging at 10% of routes, and 10% of the fast charging station placement options with a fast charging station. And in this case, adding electric roads has a massive impact on electrified traffic work. If you've already built out so 90% of options have static charging, then of course you will only have a small change by adding, also offering electric roads, but it's still a positive effect. You're still lowering system cost by taking this massive investment. Up to a certain limit where you build an absurd amount of electric road. You have so much that there is no traffic to support it. And then it drops, but you're not going to end up here. This is a very unrealistic scenario, that you've allowed everybody to build out static charging infrastructure, and then you build out an absurd amount of electric roads. The black dots symbolize where we need to be given our emissions targets in electrification, also accounting for biofuel mixing and an accelerated biofuel mixing, which we no longer have. So now the first dot is probably moving up here somewhere. In short, static charging has a lot of momentum. It's a very easy way to start. Doesn't change the system that much, but it doesn't align with any of your goals and what you want to achieve in the system. You're building to support standing still with a productive vehicle. You are cycling your batteries as deeply as possible. You're maximizing C rates. You're pumping all the energy through the battery and so on. Dynamic charging, politically hopeless to add to the system. Nobody wants to do it. Terrible investment strategy to do a massive upfront investment and then lower marginal increments. Immature standards, betting on something that isn't tested, aligns with all of your goals. So, summary. We need infrastructure. It doesn't make any sense to say how much infrastructure we need, given that there are going to be this many electric vehicles. No, we want to ensure that all the vehicles that are bought from today can be electric, because the financial part could already be done if you just had adequate charging infrastructure. If you have bad charging infrastructure, you need a massive battery, and that is not economical. If you want to minimize system cost, then you need to achieve electrification. It doesn't matter how you do it from a political point of view. You don't need electric road. You can minimize cost maybe a further 5%. But the question is, does it enable you to do this quicker? Because that is very important. The cumulative cost of running the system absolutely is impacted. So by reducing battery capacity and total battery demand, will this accelerate the transition, because you reach TCO parity with diesel much quicker, much earlier? But if this is an incentive, then you probably should also build it for passenger cars. At least if battery supply is something that holds back the transition. For instance, by driving up prices. This one is speculative. Very happy to get feedback. I believe that electric roads would be connected to a regional grid, and pretty much all other infrastructure would be connected to local distribution grid. Does that then mean that it's less grid work to build out, to enable the same amount of electrification if you add electric roads? I'm not sure. There's a cost incentive for everybody to use it, all the electric trucks. But it doesn't lower system cost that much. There is, however, this big question: if you're looking at a future system where 50% of the cost is driver, that's a very strong incentive for driverless trucks. And will they demand not stopping? Because why would they stop?
They need to charge.
Yeah, they need to charge. That's one way. But if they don't, it's always the same electric road that makes best sense in Sweden. But there might be even better solutions than the ones that are tested in the simulation. I cannot exclude that possibility. And in this simulation, it's not really possible realistically to achieve more than 90% electrification with only static charging. There is no such configuration. Is the model wrong, or is that a valid result? I'm not sure. Because it might just be that you need to change some operations instead. And then it's this question: if you're going to invest in massive fast charging stations, you need to know if electric roads will be built, because that risks outcompeting your massive investment. So you need to know that, and we don't know that today. And if you want to look at the material in more depth, you can look at this QR code. Other than that, thank you. Any questions?
Thank you very much, Jakob, for this very full presentation with a lot of interesting results and also this interesting work you have done. We now have open for questions, either here from people in the audience and also from you guys joining online. You can either write your question directly in the chat, or you can also use the raise hand function, and we will then distribute the word. But I will start off with a question we have got from the chat. It's a question about the methodology. The question is: each year or each time step in the simulation, the infrastructure is inherited, yet the vehicles are optimized anew. Shouldn't vehicles also be inherited until their lifespan has run out? Does the build out of infrastructure over time affects and is affected? I believe this is an interaction that needs to be looked at too.
Of course, it's partly motivated by simplification of the simulation, make it easier to calculate. But also vehicles can be sold to operate somewhere else. Infrastructure, not so much. So that, I think, makes this a viable, at least, way to calculate things. There is probably some inheritance, yes. It's also 5-year steps. So not that many vehicles are owned by for more than 5 years by the same owner, I think.
I can follow up with a question on that, because you have longer lifespans for battery electric trucks, but you also have battery electric trucks more adapted to a specific route or specific charging configuration.
Yes, and this is something that is a forced limitation by the input data we have with routes. The way that I think about this is that you can either optimize the infrastructure to allow for combinations of routes, or you can reallocate the transport between vehicles, given that, so that vehicle operation gets determined by local cost impact. I assume that happened today, and that's why we have today's operation. It would make sense that with a new transport system, the perfect allocation is different in some way.
Yes.
And I think if you look at the maps that are produced, in the south of Sweden, there is not much difference in terms of what vehicle you should have. There are boundaries. So if you look at above and below Mälardalen, then yes, that would be different vehicles. And then you might see some specialization there.
Interesting. Thanks. Any questions from the audience here?
It's also Estonia. Jakob, if you flip back to the last slide there in the summary, you're talking about the transition, and I'm interested in the scaling problematics. Come to the 90% electric. And on the last question there, you talk about the large fast charging stations. In Sweden, what do you consider being a large fast charging?
It seems we're looking at maybe more than 10 megawatt instead of more than 1 megawatt.
So even 10 is,
yes,
by my understanding, it's quite small.
Yes, but
so
there are
even 10 megawatt charging station would be outcompeted.
Yeah.
That would be a problem.
Yes.
You see that is this.
Yeah, but I think there are some also implicit assumptions on that you probably have load balancing through load smoothing through battery storage in some way, some energy storage.
It will help some, but you know the transportation flows are very dense to be. You stop somewhere about lunch.
Yes.
10 to 2 o'clock in the afternoon, that's lunch.
And I may have underestimated the peak there.
Yeah.
But in that case, the fast charging is going to be less attractive. And I don't think it would really change. I mean, it's not going to help the fast charging by complaining that is not realistic here, because if anything, I've made a lot of assumptions that benefit fast charging.
I'm just thinking about what's going on in the big projects as e-charge Sweden, where we set out something like 30 megawatt is needed at one of the stations in the future. And if that is sort of obsolete, why go invest in that without knowing about this?
I don't know.
And it could be sort of a hesitating. The next thing to be hesitating about investments. So I think that is an important question. Can you start out with 10 or 5 and see a ramp up over the years, or do you need to secure your 30 already? Because it's a long time to get 30 megawatts in one station.
So for the online audience, the question was about 0.9 here. We're looking today at investment plans for maybe up to 30 megawatt fast charging stations long term. And there is clearly no demand for that if you add electric roads, if I've done my math correctly. Of course, you should look at others' math as well. You shouldn't just trust me on this. But yeah, I see a concern, and I can see a concern that this would slow down investment due to the unclear lack of transparency on what the future will be like.
A second, maybe some first aid kit on that. What's your thinking about, you showed something that you see a large build out of electric road systems and also ramp up to almost 100% electrification. And you see the grid seems to be more or less the same, not the stations. But, do you have any comments about the infrastructure towards where the transportation is? Are they very different? Substations and so on along the routes. I mean,
so the question, if I understand correctly, is there a big difference for the grid?
The grid up till the transport routes.
I don't know. This is not my area of expertise, to be honest. I'm going to pass on this.
I think that is quite an interesting research.
Yes, I agree.
Sort of, road electrification.
It's definitely something that I see in my own when I try to kind of map out the system and where we would go. This is a big unknown for me.
Okay, we have more questions from the chat. Just going to take some of them. First of all, Jakob, do you have any insights into maintenance cost of ERS systems?
I'm a computer scientist. I cannot assess whether any of the maintenance costs that I get from the different suppliers are correct. The numbers I got are roughly in the same ballpark. And I'm going to have to go back to my slides because I don't remember the number. So 2% per year is approximately the number I got from the manufacturers.
And another question, have you considered the interplay between this offering and demand patterns in terms of traffic?
As I said in the beginning, it's not modeled. I would assume that if you cut transport cost by a third or half, it's going to increase truck traffic. Cannot say by how much. And you will probably see some policy measures to not increase transportation by that much in cities, but it's maybe fine in rural areas. Most of the world is not rural areas in terms of where the traffic goes. So I don't know. And I don't know how to model it. If someone knows, please contact me.
What kind of assumptions do you have regarding the price of battery components? Is it that it's going to be static or change?
The base assumption is that it will decrease a bit. I've not assumed a very aggressive curve, but still a decrease. However, even if you assume an increase, but still assume the same technological advancements, you will have a drastic reduction in battery TCO. Because you will have batteries that last longer, you don't need to have as much margin, so unused capacity. You have less weight, lots of these. You allow quicker charge rates. I don't see batteries being a substantial cost in the long term, really. But long term is maybe past 2035, 2040, 2045.
So, hi, my name is Arna from Elon Road. In the beginning, you said the reason why we're doing this is to reduce CO2 from road transportation. And I understand, of course, you have to do the cost and economics. But what would the CO2 implication or reduction be if we can reduce batteries between 50 and 80%? So what?
That's included.
In the cost, yes, but in the CO2.
I have included it in the CO2 amount. So it contributes to that. I don't remember off the top of my head, so I can say how much of the reduction is due to that, but it's included. And there are some in the report, there are some curves with different scenarios on how those result in a cumulative emissions curve versus the accepted one, or the target one. And it basically says we need to build out very fast. And we need to probably build out a lot. My belief, this again, I cannot prove, but I believe that any combination of charging, building out all options of charging infrastructure is going to achieve faster electrification than building out a subset of them. I think it might be that simple. This one also happens to be cost optimal, but it's not a big difference.
Yes, Mikael Hellgren, KTH. You had the picture about the cost for different part of was there. Yes.
I just want to clarify that this includes all the traffic. So it doesn't say we've achieved 100% electrification here. A lot of the CO2 is still from the diesel operation.
Yeah, but you have the vehicle cost, the green one, and that one is quite reduced as it looked like. I think the left one was that combustion engines.
So this reduction from this 100% combustion engine, there is no charging infrastructure, so you cannot operate electrically. And then the vehicle cost reduction that we see is partially removal of something like this part, is the removal of an expensive diesel engine, because the cost of the battery electric truck is the vehicle plus the battery. So the battery is not included in the vehicle cost, and of course the vehicle cost decreases a little.
You have a battery. There
Yeah.
you have battery as
So
well.
that's brown. A little
Okay.
difficult to see on this screen, but it's easier in the
But
report.
it's
And then, yeah, like you shouldn't see this as this is exactly how the cost will be for an electric vehicle, because it's overlaid both the diesel and the electric ones in the same figure.
Yeah, because today I think it's much more expensive with the battery
Yes,
electric truck than
and it is,
When you include the battery, yes.
Yeah.
Yes.
and that's reflected here as well.
But
It's
it doesn't
just
look like that.
so, but the thing is that
2020 doesn't, it looks almost the same. Eh?
Yeah.
yeah, but
It's not one vehicle, it's all.
it's the entire
accumulated
system,
vehicles.
the entire Swedish transport system, of which some are electric. And you have to keep in mind here that you're never going to get something that is bigger by adding infrastructure, because there's a cost optimization. So everything always chooses the lowest cost.
Yes.
You cannot, all the choices that are very expensive vehicles that increase TCO, they will be rejected and never show up in a figure like this.
And the cost for there you have it, ERS pickup. Yes.
For these other components, the ERS related components in a heavy vehicle are basically free. They don't really add much cost because you drive so much. In a passenger car, they are very substantial.
We have time for, I think, one more question and a quite quick answer. So yes, Olaf.
Okay, I was just wondering, because you can see that the battery cost is increasing first and then it's decreasing. Is it because it's increasing because you get a higher ratio of battery electric vehicles
Yes.
in the system, and then
Yes.
decreasing because of the
Cost. Yes. Was that answer quick enough?
Yes, so we actually have time for one more if it's equally quick.
I'm thinking about, maybe you mentioned that the economic lifetime of an ERS recharging point. Have you included
An
that?
ERS point.
ERS or a static charging point, the economic lifetime of those investments? Because I don't remember if you had that.
I did. Here. So the assumed lifetime of different types of charging.
Okay.
But in short, I don't see that charging infrastructure itself contributes much cost in the system. So it's not very sensitive to this. It's sensitive to battery costs. Like they achieve rough, except destination charging, that I've assumed less attractive load curve utilization, lower utilization. The other ones end up with roughly the same infrastructure cost per kilowatt hour. So you're going to have to change the components a lot. And even if ERS is allowed, in some scenarios, the cost per kilowatt hour of the electric road installation is much higher than this, by maybe 30–40%. And it's
Have you done sensitivity analysis of this?
not very much, because it's ridiculously computationally intensive. But I do know of another study by Matteo Craglia at the International Transport Forum, and he focuses instead on massive sensitivity analysis and a much simpler model. And if you look at, I've discussed a lot with Matteo, and basically I am somewhere in the middle of his assumptions. And when we consider the feedbacks, we are more towards the safe side, where electric roads are good.
Okay, I will have to interrupt there. We're approaching 9:30. It's a very interesting discussion. And first of all, maybe you can bring up that slide. So first of all, thank you very much, Jakob, for presenting this interesting work. And thank you for everyone in the audience, both here at ITRL and online. I think this work might have quite interesting implications. So let's see what this means for the future of electrification. Just to finish off, at ITRL, we around 2 years ago had another quite big seminar here around electric roads. If you scan this link to the left, you will get a link where you can rewatch that seminar. And on the right-hand side here, you have links to all our other seminars. We have quite a few of them now available. So you can learn. So yes, with that, we close the seminar. And thank you very much, and a big hand to Jakob. Thank you.